Greetings everyone, this is Team CST and this is our presentation on the final project of CS230. The topic for this project is memory cache hierarchy optimization for graph analytics. The baseline architecture that we have followed for this project is shown in the current slide. This is the default architecture that ChampSim uses. The source of the data that we used for this experimentation was all the simulations that were run on ChampSim with 30 million, nearly 30 million warm-up instructions and 60 million testing instructions. The generated simulations and their results are present in the GitHub repository. Uh, First off, we go on to experiment with different sizes of caches. Every cache level has a corresponding range of serviceable reuse distances that it can cater to, and based on various data points that we can collect through the simulations, we'll see the nature of these reuse distances and what lies within the capabilities of which cache level. So this experiment is conducted as follows. The testing sizes for each of the cache levels are changed while the other levels are kept constant. The testing sizes are half, one times, two times, four times, and eight times of the baseline size. We move on to the plots now. These are the plots for L1. Uh, as you can see, there are minor variations across various workloads, not very significant variations, but still, with increasing sizes, at least a logarithmic decrease in miss rate can be seen. For varying sizes of L2, the effect is slightly more more pronounced as compared to that in L1. And if we consider L3, the effect is even more pronounced as compared to L2. And this is the prefetch miss rate trends for the prefetch miss rate trend for LLC. From these plots, what we can understand a few insights and explain the trends as follows. Uh, as you could see in the plots for L1, uh, the plots were very insensitive towards the size of L1 cache. This shows that most of the L1 serviceable use cases, memory accesses are already handled well enough, and there is not much room of improvement here. So increasing L1D sizes is not very beneficial. Uh, the performance of code looks roughly logarithmic for two workloads, triple SP, single source shortest path, and connected components. And it is quite insensitive in the other workload, BFS. In BFS, we can see that the effect can only be seen in varying sizes of L1, not in that of L2 or L3. This shows that BFS has mostly memory accesses which can be catered enough by the L1 by the L1 cache level. This is because VFS has adjacency lists which are accessed, and once an adjacency list is accessed, it is loaded and ready for use in L1. Uh, this is a characteristic behavior of breadth first accesses, as opposed to these in triple SP and CC. We see more of depth first accesses. More details are shown in these slides. To handle these depth first accesses, we have a much greater reuse distance, and that can be seen in the L3 size sensitivity graph. L3 size sensitivity is much more for CC and triple SP. For BFS, it's again not much, and because of the reasons that I've just mentioned. So most of the serviceable cache requests of many important graph analytics problems lies in the range of L3 reuse range, and so these correspond to more depth first accesses, so that when a cache line is loaded, more depth of the nodes in the cache line are accessed before the same cache line can be accessed again, and hence the high reuse distance. And for such a situation, we can make a customized prefetcher which can handle this scenario specifically. Uh, BFS, as I mentioned, is quite insensitive towards the size of this cache level. Um, yeah, so that's it from my side. I'm Dheer Bankar. Thank you so much. I'm now handing over to Kanal.
So, hi, this is Rahul Kumar, and I'm going to be talking about the replacement policies and their effects. So, first, we are seeing the trends regarding L1D cache and L2C cache. Here we can see these are roughly insensitive towards any sort of replacement policies. And the reason being that the L2C cache and the L1C cache are too small to accommodate uh, the spatial breadth that these individual algorithms require. Yeah. So, and one more reason is that these caches are so small that no matter which replacement policy we will use, these cache lines are all going to be evicted out in in very small amount of time. So it doesn't really matter how we are evicting them because all of them are going to go out. And the next trend that I want to talk about is here's the explanation in words. And next trend is that of LLC. So there has already talked about the size and the relation of size of cache with different BFS, CC, and SSP algorithms. Here I want to highlight uh, the striking difference in the performance of LRU as compared to FIFO and LFO. So why is that LRU just obliterates the other two? So the thing is, कि there is a high degree of temporal uh, locality in all these algorithms. So LRU LRU just uh, brilliantly exploit that temporal locality, and this we can see in this graph like the for the CC it just completely I mean I think like 10 times less, and the other ones are roughly equal. So that being the reason, and yeah, so this is the explanation in words, and now I'm handing over to Kanath.
So hey, this is Kanaj Shende. So I'm going to explain the differences in implementation related to inclusive, non-inclusive, and exclusive. So the baseline implementation is non-inclusive, as we could trivially notice that there are many write back misses and write back hits at a considerable level. So basically, in the implementation part, we defined the three different implementations in FDEF and appropriately legalize them according to need. So here we are comparing the miss rates and the total misses altogether. So here we could notice that inclusive and non-inclusive don't have much difference in their at least with respect to total miss rates, but exclusive has a comparatively larger miss rate as well as the total misses. So, providing the explanation for this regarding the similarity between non-inclusive and inclusive implementations, we could see that the traces like BFS have has a slight edge over slight edge for inclusive over non-inclusive because of because of the because of spatial locality exhibited by BFS. So basically here BFS is more focused on its adjacency lists. So it tends to access memory locations which are closer to each other. So it's expected for BFS to for the cache lines to be active for longer periods of time, and thus uh, it could it could be satisfied even with smaller cost of smaller sizes of cache. So as we could say that exclusive is exactly the opposite of inclusive. So at least with respect to BFS, it shows different results. But also with respect to other traces, we could say that in general graphs tend to have cache lines retained over a longer period of time. So, regarding the theory part, inclusive tends to have close to minimal write back misses, while exclusive tends to have minimal write back hits, which is evident from this graph. So these are some of the implementations which we tried to implement, but those were too difficult or too non-trivial to implement. So I would like to just explain upon them for a bit. So firstly, one of the basic things that we could have easily done is changing the sizes of the caches, wherein it was observed even in Dheer's part ki two times of the baseline implementation, which is basically 4 MB size of LLC, provides the peak point for provides peak point for performance with respect to the cost of increasing size. Also, one of the implementations that we studied together and we thought of is key BFS. I'm sorry, graph related implementations focus have a lot of delay with respect to dependency chains. So it's very important to parallelize the DRAM accesses, thus saving a lot of time and improving IPC. So in order to do that, we could perform depth first accesses. So in this depth first accesses, we look out for specialized data that's corresponding to the particular node that we need to obtain. And if we obtain the details of that node, it would be it would be important to even access at the same time the details of its adjacency list, most the maximum possible details of its adjacency list, as as it's very likely for the processor to access them in recent times. So that's it from our side. We are team CST. Thank you.